Hello folks, in this video I will quickly go over the Coulomb force or Coulomb's law, mainly forces between the charges. Very quickly, here is the equation we have for Coulomb's force. This is called Coulomb's law. If we have two charges, Q1, Q2, if they have the same type of charge, plus plus or minus minus, they will repel as we see here. Or if they have opposite charges, they will attract. And the force on each other will be equal in magnitude, opposite in direction, as you see here and there. And the equation is a constant K, what we call electrostatic constant or Coulomb constant. K is 9 times 10 to 9 Newton meters squared over Coulomb squared, times the charges, the absolute value of charges divided by the distance squared. The sign of the charges matters if the charges are attracting or repelling. After we decide that, we draw our forces and then we drop the signs. That's what we're going to do here. And this is directly proportional to charges. As charges increases, force increases. I'm going to call it Coulomb force, and inversely proportional to the distance. If distance increases, force, Coulomb force decreases. It decreases more rapidly because with the distance squared. This is mainly talking about how the Coulomb's law looks like. Gravitational law, only gravitational force is only attraction. Coulomb force is attraction and repelling depending on the type of the charges. And how both are inversely proportional with distance. Just to remember, gravitational force was a gravitational constant times mass 1, mass 2 divided by the distance squared. And the Coulomb force or electric force is a constant K, charge 1, charge 2 divided by the distance squared. If we have more than one forces applied to a charge, like in this figure here, what we do is we find all the forces, show them in direction, and add them using vector addition. We always show an X and Y system. If we need to go components method, we find X and Y components. If we find any easier way, we go that easier way. In this figure, what we see is a force applied to charge 1 here by charge 2 is this force here. They call it F2 on 1, F2 1 here. And force applied by charge 3 is F3 on 1. And we can add those head to tail. We can take first vector, carry the second one at the end of it. And then the vector combining the first and the second vectors will be the total vector. If there's a more complicated situation, we will go a component method. This box is showing electric force and how we go about solving questions. My summary here is draw a picture, understand what is happening, and then decide on what you're going to do. Let's quickly look at some examples. The charge of sphere 2 is twice that of sphere 1. We have, let's call this Q, call this 2Q. Which vector below shows the force on 2 by 1? Force on 1 by 2 is always equal to force on 2 by 1. They are action-reaction forces. So it will be, they both are positive, so they will be pushing on each other. It will be to the left. And if this force is F, this force will also be F, or let's say 5 newtons. It will be to the left and the same size, and here is your answer. This one is asking us, we have these forces, we have these charges. Which vector below shows the force of 1 on 2? This is force of 1 on 2 at the moment. Here we see it. And which vector below shows the force of 1 on 2 if the distance between decreases to r over 2? So force of charges or Coulomb force is equal to a constant charge 1, charge 2 divided by the distance squared. If distance increases, force decreases. If distance decreases, force increases. And if distance increases by two times larger, force will be 4 times less, and vice versa. If the distance decreases to half, force will be 4 times larger, because we have force directly proportional to 1 over r squared. And if we have r to go out to r over 2, we will have, let's call this f prime maybe, will be directly proportional to 1 over r over 2 squared. That's r over 4, so we'll have 4 times larger force. It will be 4 times 1 over r squared. So we'll have the force in the same direction and about 4 times larger. Let's call this f prime. And you have the answer there. If we look at the size of this vector, none of these are shown about 4 times larger. This dude is the largest, but it's about maybe 2.5 times larger. So we don't have the answer among the choices here. There are some more similar questions. This one is asking about which of the 3 right-hand charges experiences the largest force. Again, we'll write down our equation. K Q1 Q2 over r squared, general equation here. Instead of Q1 we have capital Q here, and Q2 is either Q, 2Q. You can overall write down all the forces and see what's happening. Let's call this F1. It's a push, right? For the first option we have F1, let's say. For the second option we have F2 and F3 for the third option. Once we write down the values of forces, for the first one we will have K, capital Q, small q over r squared. For the second option, let me put it here, I have space here, F2 will be K, capital Q, 2Q, divided by 2r squared. All of this should be squared. Keep that in mind, a common mistake. So you will have here K, capital Q, 2Q, divided by 4r squared. And this will be divided by 2. So this second force is smaller than first, right? We have K, capital Q, Q over 2r squared after that. F3 similarly will be K, capital Q, 4Q, divided by 4r squared. I'm taking square of this dude, right? So it will be the same as the first one. If I divide everything by 4 here, and result is K, Q, Q over r squared. Let's put this one 2. We find F2 to be K, Q, small q over 2r squared. The smallest is F2, the second option, and the largest, the other 2 are equal to each other. 1 and 3 are equal to each other. And our option says the largest force, the largest would be 1 and 3, and they're equal to each other. So Q and 4Q are tied is the answer here. This option and this option is tied, and they are the largest. There are some more similar questions here. I'm gonna go quickly with all similar ideas. If we're asked to calculate a force, it's going to be straightforward. For this question, for example, 2 10 nanocoulomb charged particles 2 centimeters apart. What is the net force on a 1 nanocoulomb charge midway? Draw a picture. Here is your picture, plus, plus, plus. Everybody is pushing on this middle charge here. For charge 1 would push 1. Well, they call it F1 on 3 here. We can simply call it F1 as well. Force applied by charge 1 and F2, and then we find the forces. They are opposite to each other, so we will be adding them, but one is positive, one is negative. Find the total force. If we change in part B, we change the signs. We have plus, minus, and plus in the middle. Now plus on the left, charge 1 is pushing to the right, F1 on 3 or F1, and charge 2 is now pulling also to the right. Let's call this F3, and we'll add them. They will be in the same direction. Since the charges amount were the same, this will give us a 0 because equal forces opposite direction, and this will be twice. Well, add in 2 of them, so 2 times the value. And here is the solution. I'm gonna go quickly here. First one is 0, and second one we find the force, we add them. Oh, this one is A, sorry. This one is 0, and the next one is showing the option B. We find the forces. They have the same amount of charge still, although one is negative, one is positive, so they will be same magnitude of forces, and we'll add them to find this value here. This question says point A has a charge of -1 nanocoulomb, point B has a positive 4 nanocoulomb. They are separated by 1 centimeter. What are the magnitude and direction of electric forces on charge A and B? This we have the full solution on the next page, but let's call them A and B. Charge A is -1 nanocoulombs, that's -1 times 10 to -9 coulomb, and charge B is +4 nanocoulomb, 4 times 10 to -9 coulomb. And forces, they are positive and negative. Let's draw the distance in between them. That's R. I'm gonna put this aside here. It's getting too much clutter in the picture. I have 1 centimeter. Convert to meter, always divide by 100, so 0.01 meters. They will be attracting each other because one is plus, one is minus. If I show those forces, there will be an attraction force. B will be pulling on A. Let's call this FB. We can also call them F because they will be equal to each other. I know. That will be FA. Let's put also FA is equal to FB. Always action-reaction pairs. And we can calculate that force using K, QA, QB divided by R squared. And next page calculates it for you. Overall, there could be conceptual questions about the direction. We can guess the answer easily for this one, like this one here, which is the direction of the net force on the charge at the lower left, this dude here. And I'm gonna overall look at what is happening here. Everybody is positive, so everybody will be pushing. This guy will be pushing in this direction here. Ooh, let me do that better. I'll redo that. So to find the direction of force, we always draw lines and combine them. What happened here? Got out of the system somehow. Alrighty, let's find this dude. Let's erase that. So quickly I'm gonna draw lines connecting this charge, lower charge here to the others. If I do that nicely, I'm gonna have kind of this direction for this guy. I'm gonna call this force 1. And then let me use direct lines. If if I draw one from this one, it will be that, right? Something like that. So A is the direction of that. Let's draw that as well. And this dude pushes down, so C. Overall, A and C are perpendicular. When I draw my parallelogram, find the overall total to be along this line, right? This large charge was already pushing along this line. So overall, total force should be direction of B. So these type of questions are possible. I don't know what's happening here. Let's go back. Oh, this is an empty page. All right. There are some more examples, but that's general idea. There's a solved example here of a charge pulled down by gravity. That would be our mg, and pushed up by the Coulomb force or electric force, and we look at which direction it would go. Whoever is larger would win, right? On another separate video, I have several examples I go through, all similar, so I'm going kind of fast through this. Two honeybees have the same type of charges, they push on each other. What is that force? Similar questions. This one here is also a nice question. I have the solution on the next page. What happens quickly is, what is the force on charge 3? So you look at the force, the charge you're asked for, draw the forces by each charges. Charge 1 is negative, charge 3 is positive. So charge 1 will be pulling on charge 3. I'm going to call this force 1, and charge 2 positive, charge 3 positive, so charge 2 will be pushing, and we'll have two forces perpendicular to each other. They are vectors, we'll add them. I'm going to call this force 3. This is an easier kind of case. They are not in the same or opposite direction, but they are perpendicular to each other. And we use parallelogram method, Pythagorean, to solve for them. This would be the total force. Let me do a better job there. F total. And how we find it is by using Pythagorean. If two forces are perpendicular to each other, adding them is always simple because their total is equal to first force squared plus second force squared in square root from Pythagorean. And all the numbers and so on are added in here. Here we use Pythagorean to solve, and you'll find this. Try to go through these questions, look at the previous page, solve it on your own, then look at the solution to understand these better. Again, in another video, I have much more comprehensive, several examples I went through. Please also watch that video.